We are now going to look at exponential models. So here's our story. Suppose that the number of bacteria per square millimeter in a culture in your biology lab is increasing exponentially with time. On Tuesday, there are about 2,000 bacteria per square millimeter, and on Thursday, the number is increased to 4,000. So we're going to write our equation, and then we're going to predict what's going to happen in a week. We're going to figure out when do we have 10,000, and then lastly, we're going to graph this. So this is kind of the overall arching part of what we're going to be looking at. You're going to be given a story, and from that story, you're going to have to pull out your coordinate points. From your coordinate points, then you get to write your equation. One of the nice things about exponentials is based on the way we define our variables, we'll be able to make our equations a little bit easier to work with. So to begin with, we're going to need to derive our equation. So based off of the information that they gave us initially in the story, we need to be able to pull out information. Specifically starting at what's my x value, what's my y value. In the story, as you hopefully have in front of you, it says the culture is increasing exponentially with time. With time means time is my control factor. So when I start talking about time, we're talking about Tuesday and Thursday, not days of the month or the year. We're talking about weekdays. So because we do this, when we define our x value, we're going to define x as the number of days since Tuesday. And the reason we're naming it since Tuesday is that way that can be my initial zero value. Initially, before anything happened, that is Tuesday, that's day zero. And that makes my coordinate point really easy. Because on that Tuesday, there's 2,000 bacteria. So when I go down to this point here, x is going to be 0 initially because it's 0 days since Tuesday happened. And then my y value, the y value is talking about the number of bacteria, specifically the number of bacteria per square millimeter. Now keep in mind a square millimeter, how small that is. So we're talking about the number of bacteria per that square millimeter. So going back to that 0, that initial day Tuesday, that's day 0, there are 2,000 bacteria. And then Thursday, there's 4,500 bacteria. Thursday, remember x is the number of days since Tuesday. So Thursday is 2 days after Tuesday, and there were 4,500 bacteria. The equation we're going to use is y equals ab to the x, just like we worked on when we wrote equations for exponentials. And so now I have to go through and figure out what is my a value, what's my b value. Because of how we define our variable, it's the number of days since Tuesday, I always have this 0 value. And remember, when we talked about writing equations, I'm going to plug in that 0 for my x. So that's going to go in place of this x here, and then the 2,000 goes in for y. So when I do that, b to the 0 is 1, so I automatically know my a value is 2,000. Because a is 2,000, I can now plug that back in, and I can write my equation, y equals 2,000 times b to the x. Now I plug in my other coordinate point to solve for my b value. So 4,500 is the y, equals 2,000 times b squared. Divide both sides by 2,000, so 2.25 equals b squared. Now, you got to get rid of that exponent. Only way to get rid of an exponent is taking it to the reciprocal exponent, because I'm trying to solve for b. Therefore, I take the square root of 2.25, and I get 1.5. 1.5 is my b value. So therefore, my equation is y equals 2,000 times 1.5 to the x. So that's the equation we're going to be using for this story. Again, I cannot multiply the 2,000 and the 1.5 because one has an exponent, the other one does not. Now that I have my equation, I can now go through and predict the number of bacteria. So now I'm able to predict the number of bacteria by next Tuesday. So first off, I'm going to write the equation that we're using. So we're using y equals 2,000 times 1.5 to the x. Now, if that value 1.5 or the value 2,000 was not exact, you would have to grab your calculator and store that in your calculator. Store that under alpha A or alpha B, depending on which letter it is. because that's going to make a big difference when you go through and you find your solutions in the end. As I talked about yesterday, or in the previous video, when I look at finding an equation, there is, when I look to answer an equation, if I have a little bit of round off error, such as a thousandths place, it could all of a sudden be off by $1 million. And that's a big, big deal. So make sure when you are doing your story problems, if those values are not exact, you must store those. So this is my equation. So I'm trying to figure out how much bacteria I'm going to have by next week Tuesday. So if I'm looking at next week Tuesday, that's 7 days from the beginning, which means my x value is 7. So I plug in 7 for x, so therefore y equals 2,000 times 1.5 to the 7th. So take that 1.5 to the 7th, multiply it by 2,000, and I get 34,171.875. So, sentence for this. By next week Tuesday, there are just about 34,171 bacteria per square millimeter. Bacteria per. Okay, so dealing with my independent variable, which is that 7, that's the next week Tuesday part. Don't say 7 days later. What does it actually mean? That's that Tuesday. There are going to be exactly the number of bacteria we have. I do not quite have 34,172 bacteria. It's really close, but I'm not quite there yet. Okay, next example, talking about when does the number of bacteria reach 10,000. So now I have to figure out the when piece to it. So again, my equation is y equals 2,000 times 1.5 to the x. So I'm looking at 10,000 bacteria. That I'm trying to figure out when, so I'm trying to figure out x. Therefore, 10,000 goes in place of my y value. So you're getting used to now practicing solving depending on where the different unknown values are. So in this case, I've got to get my x by itself. There's 2,000 that's attached, so I divide both sides by 2,000. And I end up getting 5 equals 1.5 to the x. So now, I have an unknown that's an exponent. The only way to figure this part out is with logs. In the past, we would have tried to factor tree things, but this is not going to work out nicely. So I can either log both sides or just rewrite this into log form. So this is log, what's my base, of equals the exponent. Remember, a log is an exponent. A log is an exponent. Okay, so now I can just do change base. Log of 5 over log of 1.5. Plug that into my calculator. X equals 3.969. So now I have to figure out what does this actually mean. It's not quite 4. So it's 3.969 days after Tuesday, which means Friday evening. And if you really wanted, you could figure out the exact time if we started this, say, at midnight on Tuesday. Friday evening, the number of bacteria per square millimeter reaches 10,000. Okay. Again, rounding is important, making sure that you're not rounding too far up. Again, this is another case where, oh, it looks like it should be 4 days later, but it's just under 4 days later, which, if, again, this started at midnight, would happen at Friday evening. The last part you're going to do is you're going to graph this. When you graph these problems, look at what they're giving you to begin with. In this problem, they're giving you this coordinate point. They're giving you this coordinate point. You came up with this equation to help you as well. You came up with another coordinate point. When x is 7, y is 34,000. You came up with another coordinate point. Just under 4, it's 10,000. All of those together will make up your graph. So here's my graph. I've labeled all of those points. So as you can see, I've got my 734,000. I've got just before 4, 10,000. I've got my initial point here. I've got 2 days later point there. You noticed x, y, because that's what we used. I label my axes, okay, and I describe that point. On the initial day, there were 2,000 bacteria. Now, if you notice with this graph, I do also have an arrow going in that direction. Because we did not say we started the culture on Tuesday with that many bacteria. We just said on Tuesday we had that much bacteria. So we could have started it possibly Monday, which means I could go back here to -1. Go back to maybe Sunday. Whatever the case is, if you can keep going backwards, draw those arrows backwards. There would be a point in time where we did have to start this, but we don't know what it is according to the story problem. So this is one of those cases where arrows are fine, and it does keep going in the positive direction. We didn't stop after 7 days. We could have 8 days. We could have 9 days, etc. It can keep going in both directions. Label your axes. Label the variables we're using. Plot the graph using the coordinate points you found. And lastly, label any intercepts that are possible. And those are the second part of your story problems. Given a couple of points, graph your lines. You then also had the story problems that dealt with just exponential growth, decay, interest rates, compounding, those sorts of things. That was the other video, but this one is given some points, write your equation.